Hello everyone, my name is Jim Pasmore and I'll be presenting for Thermo Scientific the presentation called Metals ID with Handheld XRF Best Practices. I'm a consultant for them. I'm also the president of Analytical Services and Testing, and I'm the co-author of this presentation along with Jim Stachowiak, Senior Product Specialist with Thermo Fisher. So let's talk about the state of the art. This is kind of interesting for me because I've been in this business working with scrapyards and recycle locations doing testing for over 40 years. And I've seen the state of the art go from the huge OES systems and some of the early portable XRF systems to what we have today. I've been involved in the development of what we have today with a number of companies as both an employee and a consultant. So I've seen a lot of the issues and made a lot of the mistakes and learned from it, hopefully. And that's what I hope to share with you today, is some of that experience and help you to avoid some of the kind of mistakes that can be made in this business. So this slide talks about what's driving the spectroscopy use of XRF, X-ray fluorescence, and even OES, optical emission spectrometry. And we'll be talking shortly about the new technology out there called laser-induced breakdown spectroscopy, or LIBS, L-I-B-S. In any case, what do the new and entry-level sorters want? They maybe don't have the experience of 30, 40 years of traditional methods, spark testing, magnets, and so on. So they're looking for something simple and foolproof. And modern handheld sorting equipment comes close. We're going to talk about some of the mistakes you can make, but the manufacturers have gone a long way toward improving them to the point where they've become more and more robust in terms of giving you the right answer most of the time. And when it isn't the right answer, you're going to be aware of why it's not, especially as we go through this presentation, if you haven't already got that experience. Well, one of the factors that's driving it is that the cost of the new spectrometers has dropped. ISO 9000 and TQM are driving a lot of this addition of these spectrometers. Consumer requirements, they're definitely getting more stringent. They know that you can do a better job by having one of these, and so they're demanding it more because it makes their job more productive and more cost effective. Increasing frequency of penalties is one of the results of that, and a rejected load is no fun for anybody. You don't want to lose that business over the long run with more than one rejected load for sure. The payback is probably one of the key factors, of course, economics. The payback can be as short as months in many cases. I've worked with a number of scrapyards that are large enough to be able to say they've made upwards of $1 million on every analyzer they purchase over a year's time. And some of them have found some major mix-ups in very expensive loads that were wrongly marked, and maybe paid for it with just a load or two. So, you know, it's quite possible that these can be a real economic boon if you haven't already got one. This is the time to maybe take a closer look at some of those. So I talked about the old OES, optical emission spectrometry technology that goes back 40-some years. And in the early days, I saw a lot of these around. I was working with X-ray fluorescence at the time, and they were portable units. They weren't handheld like today. They were about 25 pounds, but they weren't 200 pounds like the OES. Today, everything has come down in size. OES is maybe only 30, 40 pounds, and handhelds are generally under 4 pounds. The LIBS being the latest example of a handheld at around 6 pounds. But that's taken that 200-pound OES and popped it into a handheld type configuration, and it'll do most everything the OES does as well now in a handheld configuration. That's especially important if you need to measure carbon, which can't be done on XRF. So X-ray fluorescence limitations are any element below atomic number 12, magnesium, and carbon is number 6. So only LIBS or OES can do that. And so if you've got 304, 316 L versus straight grades as an example, or a 718 where you want to know is the carbon above or below 0.15, those types of determinations are where the libs would come in quite handy. So I want to talk a little bit about the state of the art with calibration methods, because this is a pretty critical factor for you in terms of how the instrument performs in your hands. A calibration method that's empirical, as shown on the left, for OES or for libs, and some of the handheld XRF. It requires a whole series of standards, and you need to calibrate by measuring them and determining the signals for each element on each standard in each family, and then programming that algorithm or response factor into the analyzer. Now, once you've done that, it's highly accurate over a given range. The problem is that you've got to characterize every possible element in every range, in every alloy family, so it can be hundreds of standards required. It's expensive and slow, but once you've got it done, it works pretty doggone well. The better way to do it nowadays is the fundamental parameter. And the reason for that is that it takes advantage of the known, let's say, first principles of X-ray interactions with matter, and is able to develop an algorithm that simply calculates the concentrations based on the signals without having to have a whole series of standards. A few of them are used to tune it up and tweak it up for small differences in detector and tube responses. But when it's done well, it can be just as accurate as the empirical method, but certainly much more robust. That means it can handle every range from a detection limit, which is often in the parts per million range, all the way up to 100% of each and every element in each and every alloy and each and every family. So unlimited chemistry, unlimited alloy families. Fundamental parameters, when it's robust, is really ideal for recycling use, because it just has no real limitations other than sample preparation and operator skill. So how does it work? Here's a pretty nice little schematic that shows the Thermo XL5 diagram looking at the insides. And what happens is we have an X-ray tube in there. We call it the X-ray source in this diagram. It's a small miniature tube that when you pull the trigger, it's activated with a high voltage, and it shines X-rays, what we call a primary beam, into your alloy sample, which contains trillions of atoms of various elements, right? So it hits this X-ray beam hits the inner shell electron. One X-ray hits one inner shell atom electron and knocks it out. And of course, this is happening in hundreds of thousands and billions of times per second. And when it knocks that electron out, that atom is unstable, and it pulls in an electron from a higher shell. But it now has a difference in energy between those two shells. And each element, each atom, has a given characteristic difference in energy. So that energy is released as a characteristic X-ray, characteristic meaning it defines the element that it came from. That goes through a window that seals off the instrument, a very thin window so X-rays can pass through it, into a preamplifier and detector, and it's detected, converted into electrical pulses, and sent to a digital signal processor where it's amplified and converted to the type of signals that represent each and every element, and they set up a series of channels. Now these channels are where we direct each of the element signals. So chrome goes into a chrome channel, the nickel energy goes into a nickel channel, and the moly energy goes, and so on. So once we've separated those, we send that data into a CPU as raw signals, and the algorithm, the fundamental parameters algorithm, converts those signals into concentration units, displays it on the display, goes to a lookup library and says, these concentrations mean it's this type of an alloy. It's got 18% chrome, it's got 8% nickel, it's a 304 stainless. It's got 2% moly, it's a 316 stainless. It's got a little bit of titanium, it's a 321, and so on and so on. And of course it's stored in a file as well, and it can be sent wirelessly to your computers and so on. So that's the basis of it, and it's kind of important to know how it works because the more we know about the operation and the alloys, the less likely we are to make mistakes. In this slide, we're looking at the latest technology, the very latest. We're talking about 2021 technology. And here you see the two new versions of what used to be called the XL2 and the XL5. You see an example of the XL2 being used in some turnings there on the left. On the right, you see on the top the XL5 Plus, the newer version of the XL5 with a number of upgrades that we'll talk about in the next slide. And then the XL2 Plus, which we'll come to as well. So the new XL5 detector technology, what does that mean? It actually means the entire engine. The engine is the detector and the tube together, and that determines the performance along with the window material, which has to be transmissive enough to allow even light elements with their weak signals to go through. This new powerful 5-watt X-ray tube simply generates a lot more signal. And that more signal means a lot more signal going to the detector, so the detector's optimized for that tube as well. Between that and the window, light elements are tuned up dramatically. Then there's the detector guard protection that's new. If you've ever punctured a detector window, you know that's a costly problem because typically you have to replace both the detector and the tube, and that entire engine is a matched set. So it can be several $1,000s or more. And then there's new analyzer health diagnostics. So what are the benefits to you? Well, being able to detect magnesium, for example, and aluminum means you're going to simply have a faster and more accurate sort for close alloys like 3003, 3004, where there's only a small difference in magnesium. Think about aluminum and silicon in copper alloys, CDA 630. 10% aluminum, CDA 642, 6% aluminum, CDA 655, 2 to 3% silicon. All of those are going to give better performance and much faster sorting. Sulfur and phosphorus, particularly if you think about phosphorus and coppers at high levels, it's quite amenable to measuring by XRF. Sulfur in stainless steel, like a 303 versus a 304, where there's 0.3% sulfur in the 303 and none in the 304, or very low. It'll make that separation in a matter of seconds once you hit that light element filter. So it speeds the operation for light elements and tramp elements, and it separates those alloys that are very close, or what we call nearly twin alloys, much faster. Think about alloys like 17.7 versus 301. Now the only difference between those two is about 1% aluminum. So being able to separate those quickly means the difference between a huge load that's 17.7 that you've classified as 301 in the past because you didn't measure the aluminum quickly enough. And if there's a big difference in price, or your customer specifies it must be 301 or it must be 17.7, you got it nailed. So anything that depends on light elements for sorting is going to be simply that much faster. So coming to the aluminum alloy analysis, what's our goal? We want to identify as fast as possible the grades based on magnesium in general. Now, of course, in the cast aluminum, silicon is going to be a major determination for sorting. But again, that's improved as well. That's one of the other light elements that's improved dramatically. So our target is being able to do aluminum recycling much faster, 50% faster to detect 0.35% magnesium, for example, in an A356 on the XL5 plus compared to the XL5. Look at the picture on the left and you'll see the comparison. XL5 20 seconds, XL5 plus 10 seconds. There's your 50% faster to detect that 0.35%. The XL5 is designed for the most difficult alloy applications. For example, if your need is for the heavier element tramps or a difficult separation or trace elements, alloys where light elements make the difference, and they're in very small amounts. Here's some examples. 301, which is a 17.7 chemistry, but again, the only difference between that 17.7 and what's called 17.7, chrome and nickel, is the 1% aluminum in 17.7. You need that extra power to get that aluminum quickly. 303, the 0.3% sulfur versus 304 with almost no sulfur. That's a critical need for speed if you're required to separate those two. 17.4, 15.5, largely overlapping specs will definitely require highest possible sensitivity to get quick separations on that. Another difficult area is the Utamet series versus the waspaloids and the Renes. Go to the XL2 Plus for the very best in sensitivity for tramp and for trace elements. The XL2 has been the workhorse of the industry with thousands of them in use over many years, and now the XL2 Plus has enhanced the capabilities of the XL2. Even when you're doing routine sorting, it's improved dramatically. So if the XL5 is the gold plus is the gold standard, then the XL2 Plus is the silver standard. It's rugged, it's robust, it's higher performing, it's easy to use. It's got the new detector guard and turning slip-on protection. So it simply provides excellent value because it's got good performance, so you can sort all day long. Let's say that you're a sorter that's assigned 20,000 pounds in 8 hours. Well, now you're probably going to get it done in 6 or 7 hours for that same 20,000 pounds. So good sensitivity for tramp and trace elements. Not as good as the XL5 Plus, but good enough for most applications. Okay, in this section we're going to talk about challenges and solutions. There's a number of challenges in sorting, and one of them is that there's about 100,000 alloy grades out there, and they have a wide range of concentration change depending on the alloy family. Nickel alloys, for example, chrome and cobalt and nickel and iron and so on. All of those elements can change over several decades of concentration. From near 0 to 40–50%, depending on the element. And so it's a real challenge to create an analyzer that can handle such wide ranges of variation. Fundamental parameters was the solution to that. In the early days, when I was out with some of these portable XRF, with empirical calibrations, we would simply do a poor job with some of the unusual alloys, and particularly the super alloys. Very poor job. Nowadays, we do a great job with them. So 30% are the high alloy, and that's the area where you're making your money typically. And there, the handheld XRF has become the preferred method because it gives the chemistry for anything and everything. Heavy elements from about 0.001% for XL2 and XL5 Plus. Chemistry results for light elements like magnesium, as we said, down to 0.03%. So XL2 is ideal for the high temps. The stainless steels, the nickel cobalts, point and shoot ease of use, but we're going to talk about some of the things you have to be aware of when you're doing point and shoot, and you want to be fully informed as to what some of the possible sources of error are. And again, the XL5 was developed for the most demanding and most rapid sorting. So if you get a good chemistry, regardless of how many grades are out there, even if you don't get an identification, you can take that chemistry, go to www.matweb.com, and you can plug in that chemistry and get a pretty good call of what the grade's going to be. So even though the analyzer may only have a few hundred or several hundred grades of the most common alloys you're going to run into, you're never going to be completely out of business if you just have a chemistry with a no match. You can always find a source, an expert or someone else that can tell you what that chemistry amounts to. And of course, experience is a pretty good teacher, and knowledge of alloys is a pretty important aspect as a sorter. And so beginning sorters that don't have a lot of knowledge really want to have one of these handheld XRFs because they can calibrate their eyes, so for example, on surface conditions, they can begin to notice chemistries and realize what alloys they're related to, what families, and so on. So experience and knowledge is a key in using these and making sure that you're always getting good results and not getting any embarrassments. So the second challenge is dealing with a range of forms and shapes and sizes. Some examples shown here: wires and turnings and powders and drill bits and so on, fasteners, even mesh. Now XRF can handle all of that, but keep in mind that the less sample you have over that window, that measuring window, if you're not covering it fully, you're getting less than 100% geometrical efficiency. You're getting a loss of signal. So the idea is to make sure you have a good sample as much as possible over the window, and that you measure a little longer if you don't have it fully covered. That'll help to offset the signal loss. The longer you measure in XRF, the better the precision. And so longer measurements are obviously going to give you higher precision and higher accuracy. The good news too about handheld XRF is the calibrations, the fundamental parameter, is pretty much independent of size, shape, and curvature. But again, pay attention to the accuracy if you're not covering the window. An example of how to deal with something like that, take a thin wire. You've got a couple of feet of wire. Well, you cut it in several small pieces, tape it to the side of your desk so if some of it's sticking up, take the analyzer and point it right there, make sure there's nobody else around, pull the trigger, and you've got the aperture almost fully covered with several wire strands that have been taped together, and you've got the air behind it. You can't measure those wires on a table or on a bench because there's going to be other elements there that are going to be measured if you lay it down and measure it in that mode. So in a case like that, you always have to make sure there's no other sample behind it while you're measuring, because you can measure signals from substrate or other forms of samples that are nearby up to 6 millimeters away. So even if you've got a little bit of distance, you're still going to pick that up, which also means you're still going to pick up your sample, even if it's, you know, a few millimeters away from the measurement window. We prefer it to be right up against the window for best results, but it's certainly possible to measure with a little bit of a standoff. So dealing with harsh environmental conditions is another challenge. And this can be really difficult if you're in extreme conditions, extreme heat, extreme cold, rain, snow. Most of the systems today are sealed up for rain and snow. And they've dealt with high noise and low lighting by having lighted displays, and high magnetism by finding ways to shield from that. So the only thing that could really become a major problem nowadays is the extreme heat. I was working in Mexico in temperatures that were approaching 130 Fahrenheit, and you just couldn't hardly stay out there very long. And the analyzer was an earlier version of these thermo systems, Thermo Fisher Niton, and it actually overheated once we got out there for about an hour, maybe even less. But certainly I was overheated, so the solution was simply go back into air conditioning and let it cool down for a while, and then the error message goes away and you go back to work. The other solution some of them were using down there was carrying a bucket of dry ice with them, but they could stay out longer than I could. I think they're more conditioned to that kind of heat. Cold, up in the Arctic area, I've seen these things used where the display freezes up when it gets down well below zero, and the answer is they would simply open a button on their overcoat, stick the analyzer inside that open button and let body heat warm it up a little bit in between measurements, and then go back to work. So yeah, those are kind of heuristic solutions, that is based on experience. But once you've got that experience and you've learned that works, it's a good way to continue working even in the most difficult environments. So here's the probably most critical part of operating a system to get good results: the surface condition. That is absolutely critical. And most metals you can test as is. If you see that it's got a clean and a fairly bright surface, you can go ahead and operate on that sample without any further sample preparation. But remember, it's mainly a surface analysis. So if the surface isn't typical or representative of the underlying material, then the analysis will be wrong because it'll be some kind of composite of the overlying material and the underlying alloy you're trying to measure. The characteristic X-rays from elements can penetrate a few thousandths of an inch with heavy elements, but a lot less for light elements. So even the smallest bit of contamination on the surface for light elements can highly affect the results. A clean, bright metal is always best. And remember, you can have a metal coating that can look clean and bright, but it's not the alloy that's underneath. So any evidence of coating must be removed. Okay, let's talk about best practices. This is probably the heart of our presentation here. Again, alloy surface preparation, probably #1 consideration. And looking at the examples in these photos, you can see why. Obviously, paint or rust will be a major deterrent, or oxidation of any kind, dirt, scale, residuals, corrosion, and so on. Metallic dust, soil, any of these types of surface conditions have to be cleaned up before you take the measurement, or they will be part of the measurement. Here's a couple examples out of the many I've run into over the years, working in a titanium sort where they had shot blasted their CPPD titanium. And of course the reading from the XRF showed the iron pellet residue on the surface. Very high iron reading, and of course you wouldn't expect ever to see that with titanium alloys. So immediately there was a need to grind, remeasure, and find that, yeah, that iron's gone. It correctly identifies it as a CPPD. The below is an example of XRF coupons used to test the analyzer to make sure it's reading correctly. Well, if you read the one on the right, the 430 stainless that's been sandblasted, that high silicon's going to throw it off. It's going to say no match. You can't check the analyzer very well with that. The milled one on the left is going to read fine where there's no sandblasting. Obviously, you could grind the one on the right and eliminate the silicon problem. Here's some more real-life examples. Alloy surface preparation needed. Painted aluminum. That paint may be a silvery color and you're not sure if it's even painted. But as soon as you measure it and find really high titanium, you're going to have a tip-off that it's been painted, because almost every paint made has titanium dioxide as a pigment in it, along with many other pigments that will throw off the reading. So be sure to take a grind on something like that, especially if you see high titanium readings. You wouldn't ever expect to find high titanium in aluminum. These again are some of the areas where knowledge of alloys helps a lot. You know your chemistry, you see something that shouldn't be there, it sticks out like a sore thumb. The picture on the right was a real-life example, not this particular reaction vessel, but a similar one that was being recycled, and it had a nickel plating over the iron. So a novice sorter measured that and said, oh, pure nickel. Wow, we're going to get a bundle for this multi-thousand pound pure nickel vessel. Well, guess what? If you'd noticed the reading a little closer, you would have seen a little bit of iron in there. A little bit of iron says, well, that's not pure nickel. What kind of an alloy has nickel plus a little bit of iron? None that I know of. Let's grind it a little bit. And you grind it, and all of a sudden the iron reading goes way up, and the nickel goes down. It's a nickel-coated iron. And you don't want to make that kind of a mistake with any customer where there's multi-thousand pounds involved and a big cost. It's a hugely embarrassing problem if you made that kind of a mistake. So always be aware of coatings. If you even suspect it, grind it a little bit, see if the reading changes. If it does, grind it until it stops changing. Here's another example of some heavy scale on the left, Remember, it's really critical. You've got to have a clean, bright surface. And that's a pretty obvious example that even a novice sorter should be aware of. The same thing with sediment. You're not analyzing sediment, you're analyzing the alloy underneath it. Alloys that have been operated at high temperature will often have a major scale on them. If you take a look at that picture on the left, is that a copper alloy, or is that a steel underneath, or what is it? If I grind it down, am I going to get a silvery color, or is it copper? The only way to tell is to do that grinding. Don't measure over that. See what you've really got there by grinding. On the right, if you're after copper or gold in electronics, you simply cannot measure it directly on the board because you're going to pick up some of the solder, you're going to pick up some of the board material, you're going to pick up some of the alloys that you're after, and it's going to be a composite reading. So you need to take it apart in order to find out what you've really got in terms of the pure alloy. Some other examples of dirty alloys on the left. That looks mostly like rust, so it's probably iron rather than a valuable high alloy. You can, if you know for sure, by grinding it and taking a measurement. On the right, the aluminum turnings, it's not too practical to test that with XRF because you get such a low recovery when you melt them that it just doesn't make economic sense. Cautionary items include mixed alloys like turnings, powders, sweepings, etc. It's possible to use what we call the scan technique, where you might have a barrel filled with sweepings or powders. And so rather than push that analyzer down into that and take a chance on having contamination left on the window that spoils the next measurement with the added powders that are left on the window, take a little thin piece of clear plastic and place it over it. And then you can take the analyzer and hold it on the plastic and move it back and forth as you measure, and you'll get an average reading of what those powders or sweepings or turnings are. You can also put them in plastic bags to take the measurement as well. But be very aware of read-through with thin samples or samples that don't cover the aperture completely, because those x-rays are going right through there into the environment, and if someone standing in the line of fire, so to speak, they're going to get some x-ray dose, and we always want to avoid that. Two or more similar results. Oftentimes you'll see the analyzer say match 1 and match 2, and they give you a quality of match number, and they're almost the same. So that tells you you've got something going on like nearly twin alloys. You might take a longer reading to get better precision and accuracy. You might grind the surface to make sure there's no surface condition that's affecting it. And anytime you question whether there's a surface condition affecting it, just take a shot without cleaning it and a shot after cleaning it. If there's any difference in the chemistry that's anywhere significant, then it tells you you have to clean it. If there's no difference in the chemistry, it tells you grinding isn't necessary. And you can kind of calibrate your eye on whether grinding is necessary on certain types of materials after a while. And here's an example of two very close alloys. You see the Hastelloy C4 with the titanium min-max 0.03 to 0.7. And notice that everything else is overlapping specifications. So if you take a real quick measurement and don't wait for the titanium to come up, you could misidentify that. A C4 could be called a Hastelloy S. Take a few seconds longer, that titanium pops on the screen. It makes a correct identification. Instead of Hastelloy S or C4, it says it's a C4. Hastelloy S is the next closest, but the quality of match number is better for the C4. So in closing, we're going to talk about what you want to look for from supply. Bottom line, speed with good sorting. If you're faster measuring for a given set of alloys, you're simply going to have more throughput and a better bottom line. Speed is almost always one of the major considerations. Of course, it has to be good sorting, confidence in the answers with the speed. So here's kind of a list of what I think you should have as a minimum expectation. you need to make sure you're getting accurate and robust chemistries for thousands of different alloys. I'm not suggesting you need to test that many in trying it out, but take your most difficult ones, as we talked about before. If they work, they're going to be good for most of the others. Expert concierge support and training. Fast, high-confidence identification for most common alloys. Environmentally sealed and hardened. You're obviously going to be working in harsh conditions at times, so be ready for it. Detector protection via the clip-on engine guard. Ability to detect and flag tramp elements. Point and shoot, ease of use. Single piece, light, ergonomic. It should be balanced because that fatigue factor after holding it for a long time can be pretty important. And under 4 pounds helps tremendously in avoiding that fatigue factor. High power, lightweight, lithium-ion batteries should last for at least 4 hours, and most of them will be at least 6 hours and longer.
Here's 3 additional modes that can be added to these analyzers: precious metals, automotive catalytic converters, and electronic alloys for e-scrap recyclings. In the precious metals area, you can quickly determine gold carating, you can determine the gold plating thickness, and you can measure multiple different precious metal compositions, such as gold, silver, platinum, palladium, rhodium, indium, ruthenium, etc. The automotive catalytic converter application does require pulverizing of the honeycomb and the use of a test stand for the very best results. But you can do the analysis of the platinum, the palladium, the rhodium, and more. In the electronic alloys or e-scrap recycling, this latest technology can help you recover the materials such as gold, platinum, silver, nickel, palladium, rhodium, copper, iron, and aluminum, and so on. And finally, the small spot collimation and the camera option allows you to analyze smaller individual electronic components, maybe directly on the PCBs, and avoid some degree of disassembly. So all of these modes can be added to the existing analyzers. Check with the factory for pricing on those.
So here's our final slide, a summary before you buy. Some of the things you want to consider. The reputation and confidence in the supplier. Is it going to be around over the long term? Is it likely to be sold, as some of them have in the past, and change the support capabilities? What kind of expertise and quality of service do they have? What's the reputation? What's your cost for downtime? How long might you be down? The speed of testing. The frequency that you're going to use it, that determines the productivity and the profits that you're going to make from it. Your light element and tramp element capability. The robustness, is it sealed? Is it hardened? How about the calibration? Is it fundamental parameters and therefore robust? Do you have a good wide alloy grade library? And does it make the right call? If you've got a couple alloys that are real close and it's making the wrong call, the grade library isn't optimized. So check for those kind of things. Ability to separate nearly twin or close alloys, and no charge on software upgrades. Bottom line, and this is what you really want to do before you buy, most important, test it in your yard on your toughest samples and in the toughest conditions. Once you've confirmed it under the worst case conditions, you can probably make a pretty good purchase with good confidence. So thank you very much for listening. If you have any questions, please let us know.